Alright, so in this video we will present a proof of Cauchy's theorem. Now remember that in a previous lecture we have actually already established Cauchy's theorem for abelian groups. Precisely, we proved that if G is an abelian group and if P is a prime number which divides the order of G, then G necessarily has an element of order P. So in other words, to again explain what is being said here, we have shown that if P is prime, G abelian, and P divides the order of G, then there exists some element G such that the order of G is actually equal to P. Okay, and this is Cauchy's theorem. Now what we'll try to do is prove this when we replace G with just any group. This result is actually true when G is not abelian as well. Right, so again, we'll generalize this result to the class of all non-abelian groups. But before we get to that point, this requires some work. So, as a starting point, we'll talk about the concept of an orbit. So, let's S be a finite set. Recall that AS is the set of all, when we say AS, we mean the set of all functions f which are mapping S into S, and F is a bijection. We will define a relation on our set S, and for this relation, let me explain exactly what this relation is. We'll say that two elements X and Y are related to each other if and only if X is of the type f of F and so on of f of y for some integer k, where k is the number of time we actually composing f. So this will be, so f, this will be k times. Okay, so in our shorthand notation for f composed with itself, k time is f power k. Okay, so again, we'll say that x is related to y if and only if there exists some integer k such that x is equal to the composition of f k time. Now keep in mind that in the case where f is in the case where k is negative, then so for instance, when we write f of -2, what we mean is the inverse of f composed with itself twice. Okay, so in the case where k is negative, then you can think of when we write fk, then what we mean is essentially f inverse composed with f inverse the absolute value of k many times. Alright, so it is a fact that this actually defines a relation on the set S. It defines an equivalence relation, on the set S. And the orbit of an element X is the equivalence class of X. Okay, so the orbit of an element X will be essentially the set of all elements of the type fk of X where k is an integer. Okay, so the idea is, if you start with, let's say, an element x, then we want to look at the equivalence class of x, then you apply f of x, f of x, and you keep going indefinitely. You apply the inverse of f, the inverse of f twice, and so on, and you keep essentially just going. Next you'll have the inverse of the inverse of the inverse of x, and next here you'll have f of f of f of x, and you just keep going indefinitely in every direction, right? So this will be an orbit of x, or the equivalence class of an element x in the set S. Let's look at some example here. Suppose we have the set S, which contains for elements 1, 2, 3, and 4. And let's suppose we have a map F which sends 1 to 2, 2 to 3, 3 to 4, 4 to 1. And clearly the inverse of F will send 1 to 4, right? 2, notice here, to 1. 3 goes to 2, and 4 goes to 3. Okay, so we will say here that x is related to y if and only if there exists some integer k such that y is fk of x. Okay, so suppose we start with the element 1, right? So notice that 1 goes to 2, right, through this map here. And then what happens to 2? 2 goes to 3, okay, and 3 goes to 4, and 4 goes back to 1. So this tells us that the orbit of 2, or the equivalence class of the element 2, is the set containing 2, 3, 4, and 1. Now, notice that this is actually all of S. So in this example, we have one orbit. Or in other words, we have one equivalence class. So that means that with respect to this relation that we have defined, any element in the set, any two elements in the set S are related. All right, let's consider another map F, again, which is a bijection, which is sending 1 to 1, 2 to 4, 3 to 3, 4 to 2. So essentially, the map F fixes the element 1 and 3 and swap 2 and 4. So if you were to compute the inverse of F, you will agree that we will send 1 to 1, right? 2 goes to 4, 3 goes to 3, and 4 goes to 2. So clearly, in this map here, for this map, the inverse of F is actually F. All right, now let us compute the orbits of an element. If you take 1, 1 goes to 1. Okay, so that means that the equivalence class of 1 is 1, because if you keep applying iteratively the map F of its inverse, you simply just get 1 and 1 and 1 again, right? So in other words, for any k, which is an integer, fk of 1 is always 1. Okay, similarly, you can also see that fk of 3 is always 3, because 3 maps to 3, and then if you iterate the map again, you get 3 over and over again. On the other hand, 2 goes to 4 and 4 goes to 2, and any other iteration is only going to give you one of these two elements. So the equivalence class of 2 contains 2 and 4. The equivalence class of 3 is just 3, and the set containing 3. And the equivalence class of 1 is just the set containing 1. So in this example, we have 3 distinct orbits, 1 orbit of 2 elements, and 2 orbits of 1 element. In this case, let us consider an example of a set which is actually infinite. Let's suppose S here is the set of all real numbers, and AR is the set of all bijections of R onto itself. So suppose we consider the following bijection. We consider f of x to be 2x, and you will of course agree that this is an example of a bijection, right? All you have to do here is show that this function is one-to-one, it's injective, it's also surjective. All right, now notice that if you try to compute f of x, what do you get? Well, that's f of 2x, but then f of 2x is 2 times 2x, so that's 2 square of x, right? What if you want to compute f of x? That'll be f of 2 square of x, which is 2 times 2 square of x, so that'll be 2 cube of x, right? So then generally for any natural number n, or you will agree that f composed with itself n time applied to x is just going to be 2 power n x. All right, now if you compute the inverse of f, and remember from pre-calc how to compute the inverse of a function, you set f to be equal to 2x and you solve for x. When you solve for x, then you get that x must be y over 2. So the inverse of the function will be f inverse of x will be then x over 2, which you can also rewrite as 2 power 1 x. And then you can check also that in this case for any natural number n, the composition of the inverse of f with itself n time is just going to be 2 power negative n x. So generally what we have shown thus far is that for any integer k, fn of x is essentially just 2 power k x. So this tells us that the orbits, if we want to compute the equivalence class of x, or the orbits of x, this will consist of all real numbers of the type 2 power k times x, where k is an integer. All right, so given f, which is in AS, the order of f is the smallest positive integer for which fn is the identity map. So when you write the order of f, this is the minimum of the set of all n such that fn is the identity map. Okay, if this is not the case, if this minimum doesn't exist, then we'll say that the order of f is simply infinity. Okay, now in this lemma we'll prove the following. If f is a bijection on S and is of order p, where p is a prime number, then the orbit of any element of S under the map F has either one or p many elements. So the proof goes as follows. Let S be an element of the set S, and if f of S is equal to S, then clearly S is fixed under the map. So then the orbit of S will be the singleton containing S. Why? Because for any integer k, it will be the case that fk of S, right, will be f of f, say of f S, or it will be f k of f, or fk of S will then be f inverse of f inverse, and so on, of f inverse of S, the absolute value of k time. Notice that at each time you're getting S, right? So this here will be S, and then when you apply again F, you get S. This will be S. When you apply f inverse again, you get S. No matter how many times you apply the function f of f or f inverse, you will always get S, right? So that tells you automatically that the orbit of S is the singleton containing S if S is fixed under the map F. Now, suppose that this is not the case, right? So suppose that f of S gives us another element. Now we consider say the sequence S, f of S, f of S, all the way till we compose f with itself p minus 1 many times, and we applied all of these functions to S. Then we hope to show that this set here has precisely p minus 1 many elements. Okay, so in other words, none of these elements here can repeat themselves. That's the idea. So every single time that you are applying f, or in a composition of f with itself j many times, you're getting a distinct element until you hit p minus 1. That's what this is saying. Okay, well, so otherwise, suppose otherwise that this set does not contain p minus 1 element. What that means is that you must be able to find two positive integers, k and j. K is strictly smaller than j, and j is no more than p minus 1, such that when you compose f with itself k time and you apply S, you are eventually getting this. Now, if you take this equation and you compose it with the inverse of f of k, so this will be f of k inverse compose of f of k of S. This will be equal to f of k inverse of fj of S. But then this is essentially equivalent. Notice that the left hand side here is just going to be S, and the right hand side is going to be f negative k of fj of S, which is fj minus k of S. Okay, so we should get that as we computed here. So we should get that S is equal to f of j minus k of S. Now j minus k is positive, so let m be equal to j minus k, where m is going to be a strictly positive number. Then what we are saying is that fm of S must be equal to S for some positive integer m. Now, since P is the order of F. P is the smallest number such that satisfying. So again, P is the smallest number such that Fp is the identity, right? So what this is saying is that but since F is of order P, then it must be the case that F of P of S is equal to S, right? Okay, well, now since P does not divide M, then that tells us that P and M must be relatively prime. So in other words, we should be able to find two integers a and b such that AP plus BM is equal to 1. All right. Now, so what this is saying is you can rewrite F of 1 S as simply just F of S, right? But then 1 is AP plus BM of S. Okay, so by assumption we know that Fm of S is S. So this here will be just S. But then this here has to be S. Why? Because we know that F of P of S is S. So far what we have obtained is that F of S must be S, which contradicts the assumption that F of S is not equal to S. All right, so this violates our assumption and this gives us the desired contradiction. Now, Cauchy's theorem says that if P is a prime number and P divides the order of G, then G must contain an element of order P. Okay? And this is for any finite group. So let me again try to explain what this is saying. So let G be any finite group, and let P be a prime number such that P divides the order of G. Then Cauchy's theorem says that there exists an element G in our group such that G is of order P. Okay, so let us substantiate these results. First, we'll look at the case where P is 2, the smallest prime number. So the fact that 2 divides, since 2 divides the order of G, this is telling us that G must be even, right? I mean, the order of G must be even. All right. Now, I will consider the sets S of all order pairs of the type X inverse. So we're essentially pairing every element with its inverse, assuming that X is not the identity element. Okay, now if S only consists of order pairs of the type XY, where Y is distinct from X, then there exists some natural number R such that we can rewrite G as follow: X1, X1 inverse, X2 inverse, all the way till XR, XR inverse and then E, right? So we're saying that if all possible order pairs in the set S consist of distinct elements within the pair, then G can be enumerated as follows. But if you are to count then the number of elements in the set G, then you will get that the order of G is 2R plus 1, which is odd, right? And that can be the case because we assume that G is even. So that's the idea. So then that tells us that the assumption that S only consists, this assumption here that S only consists of order pairs of the type XY, such that Y is distinct from X, can't be true. So in other words, there must exist at least one element of the type XX which is in the set S. Okay, but the fact that XX is in the set S, by definition, if you look at the membership requirements of S, this forces X to be equal to its own inverse. But when this is the case, if you multiply on the left hand side by X, you get XX is equal to XX inverse, which is E. And this is essentially equivalent to stating that X square is E, right? So that tells us that there must exist an element of order 2. Okay, so in other words, the order of X here is 2, confirming Cauchy's theorem. Okay, so we have just proved Cauchy's theorem under the assumptions that P is the smallest prime number. Now let's look at the case where G is 3. So in this case, let's consider the set S of all triples of the type X, Y, and Z, where X, Y, Z is in G, and additionally, if you take X, Y, Z, you get the identity. Now, the fact that X, Y, Z is equal to the identity, in fact, implies that Z must be X, Y inverse E, which is just X, Y inverse. And when we apply the inverse, you get here Y inverse X inverse, right? So this is telling you that S is actually a set of triple of the type XY and Y inverse X inverse, where XY is in G, right? So somehow there is a relationship between X, Y, and Z. All right. So since Z depends on just X and Y, then so that means that if you want to count the number of elements in S, let's see here, we say we have here X, Y, and Y inverse X inverse is in G. Well, it won't really matter what is happening in the third component, because the third component depends on your choice of X and Y. So if you really want to count the elements in this set, you just need to focus on the first two components. But there are the order of G. If you say so, there's sort of order of G many ways of choosing X, and for each of these choice there is again the order of G many ways for choosing Y. So this is telling you that the cardinality of S is essentially the order of G squared, right? That's how many elements, that's how many distinct elements you can have in the set S. All right. Now, we will define a bijection F such that the bijection will take the triple X. This is a bijection on S. You'll take the triple X, Y, and Z and move it, sort of move this around. So move Z first, and then x comes second, and then y is third. Okay, and I want you to pause the video and check. This is an exercise, so prove that the function f which map S into itself is a bijection. Okay, go ahead and prove that. Now, by assumption, we say that P is 3, right? And 3 must divide the order of G. That's our assumption. So we can find at least 2 distinct elements x, y in G, and setting Z to be xy inverse. Then if you take f of x, y, z, which will be f of x, y, xy inverse, the function f acts on this element and gives us xy inverse xy. And I claim that this can't be its input. Right, so the image of xy inverse can't be its input. Why? Because if this was the case, then x must be equal to y. But by assumption, we assume that that's not the case. All right. So in other words, this function does not fix this element. So this shows that f is not the identity element, right? It's not the identity element because it at least maps one element to an element which is not the input. Also, if you look at f of x, y, and z, we said that this was z x, y. Now, if you compute f of x, y, z, what do you get? You get f of z x, y, which will then be y, z, x. And if you compute f of x, y, z, you get x, you get essentially f of y, z, x, which is x, y, z. So this shows that f3 of x, y, z is equal to x, y, z. So f3 must be the identity map. It's the map that takes every point to itself. But 3 is the smallest positive integers for which f3 is the identity. So that tells us that 3 has to be the order of the map f. Okay? Now, by the preceding lemma, any orbit under the action of f will have 1 or 3 elements. We've seen this earlier. That was the lemma that we proved. Now, since S must be partitioned in its orbit, the cardinality of S, which is the number of elements of S, can be computed as follows. Let n be the number of orbits with 1 element, and let m be the number of orbits with exactly 3 elements. Then the cardinality of S has to be n times 1, right, plus 3 times m. That's precisely n plus 3m. And this, we saw, is the order of G squared. Now, solving this for n gives us that n must be the order of G squared minus 3m. However, so notice that 3 divides 3m, and 3 divides the order of G squared. So that means that 3 must divide n. But what does that mean? Remember that n is the number of orbits with 1 element. Well, since 3 divide the order of G, right, again, we saw that it follows that n must be a multiple of 3. And this means that there are at least 3 distinct one-element orbits, and one of them is given by the triple EEE. For sure. Why? Because the orbits of this element is always is the set containing with itself, right? Because no matter if I start with E, 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 and I apply F, I'm always going to get E, 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 and generally for any integer k, Fk of E, E, E is always going to be E, E, E. Okay. But there are other elements, because we saw that n must be a multiple of 3. So we can choose x, y, and z, which is not E, 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 such that the orbit of x, y, and z is a set containing one element. Okay, so clearly f0 of x, y, z is just the identity. So this will be x, y, z. And if you take f of x, y, z, that will be z, x, y. And if you take f of x, y, z, this will be f of z, x, y, which is y, x, which is y, z, x. And all 3 of these must be the same. So in other words, x must be z and that must be y if all 3 of these triples are equal to each other, because they belong to an orbit, they belong to a one orbit element. So they must be exactly the same. So so far, so we have obtained that x, y, z has to be x, 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 right? So, but then x times x times x, that's x cubed, that's E, right? So x must satisfy x cubed is the identity. And since x is a non-identity element, x must be of order 3, okay? All right, so, and that's exactly what we want. We have just find an element in the group which is of order 3 when we assume that the order, when we assume that 3 divides the order of the group. Now, the general arguments when P is prime and P is strictly greater than 3 is really the same idea. If we mimic this process, these arguments, and we generalize them to arbitrary prime numbers, we'll get the exact same result. But I find that it is actually a lot more illuminating to look at this example to really understand what is happening. So I will leave the general case for you to read from your textbook to try to make sense out of. All right. Now we've proved Cauchy's theorem. Now we'll look at some nice result that we can deduce from Cauchy's theorem. In this result, suppose that G is a group of order P times Q, where P is prime, P is greater than Q. Okay, so the order of G is PQ, P is prime, and P is greater than Q. Then according to this theorem, G has a unique subgroup N such that the order of N is P and N is normal in G. All right, so by virtue of Cauchy's theorem, since we assume that P divides Q and P is prime. So there must exist an element X, right? So there must exist some element X in G such that the order of X is actually equal to P. That's Cauchy's theorem. Next, let N be the subgroup of G, which is generated by P. So we think of which is generated by X. Think of N as being this element. Then we first aim to show that A is unique. Suppose otherwise. So suppose that there exists a subgroup M which is distinct from N, which is of order P. So somehow suppose by contradiction that there exists M and N. M and N are not the same set, and the order of M and the order of N are equal to P. We assume this by contradiction. Now, since P is prime, we know that any group of order prime is cyclic. So M is necessarily cyclic. So we argue next that the set NM, whatever this set is, has precisely P square many elements. Now, by construction, since N has P many elements and M has P many elements, by construction, it's clear that NM has at most P square many elements. What we need to prove here is that somehow we are not getting some repetition by taking arbitrary product of elements of N and M. Okay? So to prove this, let's suppose by contradiction that there exists N and M, U and V in the product NM such that somehow, so we want here N and U to be in N and M and V to be in M, and somehow N times M and UV is in NM and NM is actually equal to UV. So somehow we're able to take distinct pair, put them together, and we get the same elements. We want to show that this is not possible. So the fact that NM is equal to UV implies that U inverse N must be V M inverse, right? So what does that mean? If you look at U inverse N, okay, and you look at V M inverse, remember that U and N are in, so we saw that U and N are in N, and M and V are in M. So U inverse of N must be in N by closure, and V M inverse must be in M. And the fact that these two are the same implies that, so the fact that U inverse N is equal to V M inverse implies that both U inverse N and V M inverse must be in N intersect M. Okay, so you take the overlap in between these two subgroups, and we have an element inside this group. So one can show, please pause the video and show for yourself that if N and M are subgroups, then the intersection is also a subgroup of both groups. So now N and M is a subgroup of N, and M is also, so N and M are both is a subgroup of both N and M. So that means that the order of n must divide p, which is a prime number. So that tells you that the order of n intersect m is either 1, or the order of n intersect m must be p. We only have two options because p is prime. Now, if the order of if somehow the order of the intersection n intersect m is p, then that means that the overlap gives us everything, right? But if the overlap gives us everything, this is implying that n must be m, which is n intersect m. And that would be a contradiction because we assume that n is not m. Okay, so since the order of n intersect m is not p, since the order of n intersect m is not p, then the order of n intersect m must be 1. Okay? But this will mean that u intersect n must be v m inverse. I'm sorry, this will mean that u inverse n must be v m inverse must be e. But this will imply that u must be n and v must be m. But this will mean that the pair nm must be equal to the pair uv, again contradicting the assumption that nm and uv are distinct pairs. All right, so this shows that m has exactly p square many elements, and I'm sorry, this shows that nm has exactly p square many elements. But then this will imply that p square is less or equal to pq, right? Because nm is contained in G, which has order pq. And p must then be less or equal to q, right? If you take p times p is less or equal to pq, and then you divide by p, you get that p is less or equal to q, contradicting the assumption that p is strictly larger than q. Aha. So therefore n must be unique. The assumptions that n is not unique is false. Okay, so n must be unique. Now let G be an element of G. Then the conjugate G and G inverse is a subgroup of G. Moreover, if you look at the map, if you look at the function phi, which sends G and G inverse, again, this function is mapping the conjugate of n into n, such that phi of G n G inverse is equal to n. I would like you to pause the video and to show that phi is a bijection. Okay, prove that phi is a bijection. The fact that phi is a bijection, once that's established, this will show that G n and G inverse, they both have the same order, right? They must have the same element, and that's P. By the uniqueness property established earlier, it must then be the case that G n G inverse is n, but this is precisely what it means for n to be normal. This will imply that n is normal in G. Okay. All right. So suppose that G is a subgroup of order PQ, P times Q. P and Q are here prime numbers, and P is strictly bigger than Q, and we'll assume that Q does not divide P minus 1. If all of these assumptions hold, then we'll prove that G is a cyclic group. So it's generated by just one element. Okay, so, well, according to Cauchy's theorem, G has an element X of order P and another element Y of order Q. Now, since the group generated by X is normal and has prime order, then it has to be cyclic. So, in other words, the element Y, the conjugate of X by Y, has to be an element of the cyclic group generated by X. What this means is that Y inverse has to be equal to xk for some k, which is an integer. All right. And of course, k is in between 0 and p. Now, let us take a look at y square x y negative 2. Well, you can rewrite this as y x y inverse, and let us just look at the inner group, this here. Well, by assumption, that's y xk y inverse, right? Now you can think of that as y x k many times y inverse, and in between, so you can put here, let me notice that I'll rewrite this as y x, and then I'll put y inverse y in between each x, again y inverse y x, and you keep playing the same game until here somewhere you'll have again y, I guess you'll have y inverse here y, and then you'll have x y inverse. Now we'll group. Look at this group here. Well, that's x power k. That's another x power k, and you keep going until you have k many of those, right? So in summary, what we'd have here is the following. You'll have xk k many time. Well, that's xk time k, which is xk square. Okay, and more generally, so for any j which is an integer, it'll be the case that yj x y negative j is going to be xk to j, to power j. Now, in particular, if we write x as exe, and because y is of order q, then this will be yq x y inverse of q, which will then be x power kq. And the fact that since we see here that x kq is equal to x, this will mean that x kq x inverse must be e, but this is really saying that xkq minus 1 is going to be e. Okay, now this will implies that, so we have so far that xkq minus 1 is e, but p is the smallest number satisfying x power n to be E. Any other number has to be a multiple of P. So that tells us that P divides KQ minus 1. Okay, so moving forward, the fact that P divides K power Q minus 1 means essentially that you can rewrite KQ minus 1 as PL for some integer L. Okay, but then that really means that K power Q must be 1 mod P, right? Why? Because you can rewrite KQ minus 1, you can rewrite KQ as PL plus 1. So that means that when you divide KQ by P, you will have a quotient of L and a remainder of 1. Okay, so that's why KQ must be 1 modulo P. Now, regarding K as an element of the multiplicative group 1, 2, all the way till P minus 1, endowed with multiplication modulo P, it follows that the order of K must divide P. Why? Because we're saying here, so if we say that we regard K as an element of this group, but this group has order P minus 1. Now, what we've shown here is that KQ is 1 modulo P, right? So we saw that KQ is equal to 1 modulo P, and Q is a prime number. So Q has to be the smallest number for which the power of K is 1. So that tells us that in this group, the order of K must be Q. Now, since Q is prime, the order of K must be either 1 or Q. Why? Because K is an element of a group of order P minus 1. Right? So K has to divide, Q, and Q is prime means that either K is 1 or K is equal to Q. That's all that this is saying here. Right, so, but the order of K must also divide P minus 1. Okay, why? Because K is an element of a group of order P minus 1. Now, so Q does not, since Q does not divide P minus 1, the order of K cannot be equal to Q. Okay? This forces K to be 1, and as a result, if you have yx, y inverse, that has to be equal to x. But then multiplying the right hand by y, if you multiply the right hand by y, you get precisely yx, right, must be xy. Okay, so let z be equal to xy. By assumption, the order of z must be either 1, p, q, or pq, because z is an element of G, and G has for order pq, and p and q are prime. So since x and y generate disjoint subgroups of G, the first three options are out of question. So what we're saying here is that x and y, they generate group of order P and Q respectively, and those groups can't have any, they have a trivial intersection because they are of order prime. So the element xy being generated by the element x and y, it can't be in one or the other, right? It can't be in one or the other. It has to be necessarily its order has to be PQ. So this shows that Z has for order PQ. So we have just found an element of order PQ, but G has order PQ. So that tells us that G is generated by Z, which is XY. So G is cyclic. G is a cyclic group. Finite group of order 15. The prime decomposition of 15 is 3 times 5. 3 and 5 are prime numbers, right? 3 and 5 are prime. Five is greater than 3, and 3 does not divide 4. Okay? Then automatically we can conclude that G is a cyclic group of order 15. So this, again, we have completely characterized all groups of order 15. There's only one of them. Any group of order 15 has to be cyclic. And here is the Cayley diagram of a group of